two small demos. We manufacture two small demonstrators, a glass fiber epoxy and a glass fiber helium. And I'll just talk about how I manufacture those. Structural testing of the two demonstrators will be presented by Yadong. Design of a highly efficient wind turbine blade, again by Yadong. Recyclable wind blade manufacturing will be presented by myself. Testing of the full-scale recyclable wind blade will be handed over to Yadong, and followed by summary challenges and recommendations. So my name is Conor Kelly. I'm an engineering team lead at ÉireComposites. Since 2020, that's when I graduated from the University of Limerick with a Master's in Mechanical Engineering. I'm involved in several projects funded by Horizon Europe and SCA Ireland. These include Marewind, Blade to Circ. They're about sustainable wind blade materials. And Multum then is another composite project about 3D printing and additive manufacturing. Fastship then is another, it's a marine based project where we fit bow foils to ships to try and reduce drag and reduce fuel consumption. Deep Wind Demo, vertical axis wind turbines. LE Protect is leading edge protection. And Sustablade then is also about sustainable blade, wind blade materials. My contact details are there. Give them over.
Okay, so I am Yadong. I'm a lecturer in civil engineering of University of Galway, and my research mainly focuses on the design and manufacturing of large complex structures like the wind turbine blades, tidal turbine blades. I'm also interested in the numerical modeling of the tidal wind turbine blades, and we designed the software called BladeCom to optimize the performance of a rotor blade. And in the past, I have been involved in many projects related to the renewable energy, not only wind turbine blades, but also tidal turbine blades, different type of turbines, and both carbon fiber and glass fiber. And here in this presentation, I will just focus on the Waveblade project, which is full-scale wind turbine blade made with glass fiber and some recyclable material. So there as well. Nice. Okay, and I'm from the Sustainable and Resilient Structures group here in University of Galway, which is funded by Professor Jamie Goggins and led by William Finnegan. And in this research group, we have focused on a lot of different aspects, like the design testing of large-scale complex structures, not only in the blades, but also the domes, some parts for the satellites, and also wave energy converting devices. And besides that, we also have been interested in the studying of the building energy efficiency and some structural designing of houses for earthquake seismic active zones, and try to achieve sustainable and resilient structures. And now I will hand it to Conor for the project.
Right, thanks, Yadong. So now I'll just give a project overview. So by 2030, 70% of Irish turbines will reach end of life. This will be a major issue for landfill or trying to find ways to recycle these. So Reblade will develop technologies to retrofit and upgrade the existing Irish energy stock, and that will enable Ireland to reach its carbon targets and promote sustainable living. This is how we plan to do it. So a turbine will be decommissioned, and it'll have a set of end-of-life blades, and we'll try and recycle or recover them depending on the type of material that we're using. And then we'll redesign the components, such as the shell or the skin, to try and capture more wind, or the structural components, try and reduce the weight so that we can recover more power. And then we'll manufacture these blades, retrofit them to the existing turbine towers and nacelles, and then install them and get them up and running again. Then the project aims to create new, highly efficient and resilient blades to extend working life while reducing their weight and increasing power production. And then the expected environmental impact is to try and remove 8,260 million tons of CO2 by 2030. The project is a joint partnership between ÉireComposites and the University of Galway, where ÉireComposites are the blade manufacturer and University of Galway are the blade designers and structural testing. So the project objectives for Reblade is to design a highly efficient and resilient wind turbine blade, which is designed using the BladeComp software developed by the University of Galway, and hopefully suitable enough to reblade Irish turbines. Then it's to de-risk the design through structural testing of both demonstrator and full-scale wind turbine blades, to develop high-volume production manufacturing processes for these new wind turbine blades. I'll talk about that later when we're talking about the manufacturing processes. And the final objective is to explore commercial opportunities and new markets within Ireland and Europe to expand ÉireComposites' customer base. So the project flow. So initially we created a preliminary wind blade design. So we had materials to select from, which included the epoxy and helium resin with glass fibers, and then we created a preliminary or the initial wind blade FEM model. Then we moved on to selecting material and validating the initial finite element model. So to do that, ÉireComposites did the design and manufacture a demonstrator, a 5-meter long demonstrator, and the University of Galway then tested it. So we had 2 demonstrators, one glass fiber epoxy and one glass fiber helium. Then once we got the test results and validated the FEM model, we did a final wind blade design and finite element model. And then that brought us on to the final step of the project, which is structurally validate the new wind blade design and the finite element model. So ÉireComposites designed and manufactured new tooling or molds and manufactured the wind blade, and then University of Galway then received the wind blade and tested it in their structural testing facility. And that's what it looks like from a CAD perspective. Wind blade material selection. So what is a composite material for people that don't know? So composite is when you combine 2 materials with similar properties, and then the resulting material then has superior properties. So for example, glass fiber fabrics, when you combine them with resin or matrix or plastic as a binder to hold the fibers together, you get a composite material class called glass fiber reinforced plastic. So glass fiber is the main reinforcement that we're going to be focusing on today. And then the resin system or composite comparison is made in this table. So the epoxy resin is a 2-part system. It just has the epoxy resin and its hardener. And then the helium resin is a 3-part system. It has acrylic resin plus an accelerator and then a peroxide hardener. Then all the other properties are very, very similar. The viscosity is quite similar, although the helium resin has a lower viscosity, which is more beneficial for infusion. It can penetrate fibers much easier than a higher viscosity resin, such as the epoxy, although they're fine. Tensile strength is very, very similar, as well as the tensile modulus, compression modulus. They're all in around the same values. One has a higher tensile strength, but a lower modulus, and similar for the compression modulus. The recyclability then in terms of sustainable material. Epoxy obviously is not recyclable, not yet anyway, whereas glass fiber helium is because it's a thermoplastic, so we can reprocess it and recycle it as many times as we want in theory. So then wind blade manufacturing process. So the manufacturing process that we used was the vacuum assisted resin transfer molding process, VARTM for short, or other people know it as just the infusion process. So this is just a quick diagram that I got from Gurrit, who supplied the epoxy resin. So as you can see here, you have your resin pot here, which contains your resin, liquid resin. And then you have your mold tool. The purple line is your reinforcement stack or your dry glass fiber or carbon fiber, whatever fiber reinforcement you want to use. The yellow line is your peel ply or resin distribution fabric. That's to encourage the resin to penetrate the fibers and flow across your material and flow across from one side of the mold to the other, to the vacuum pump at the outlet. So yeah, when you turn on the vacuum pump, you will suck resin from the resin pot and into an inlet, which is kind of a port in your vacuum bag. As I mentioned, the vacuum bag here is this purple line, and the sealant tape is what seals it so that the air doesn't get in or out. So yeah, as the air is basically leaving the bag and creating a vacuum, it creates a pressure differential and it sucks resin from the resin pot through your mold, and your dry glass fiber wets it out, and then you just shut off the valve once everything is wet out. So then this brings us on, once we have the process selected and the material selected, brings us on to the demonstrator design. So we chose a 5-meter box bar demonstrator, which is representative of, I'm not sure if that's in the way or not, here. So we chose a box bar as our demonstrator because it's the structural component of a wind turbine blade. It's basically the spine of the wind turbine blade. And that's where it gets all its structure. So it's the best component to use to test new material and validate numerical models. So we selected a 5-meter long box bar so that we could get some good deflection in it. And so it contains 2 spar caps, 2 webs, and then 22 metal inserts or T-bolts, depending on which demonstrator we're talking about. And it's all adhesively bonded together. And the adhesive is different as well. There's a Spabond adhesive, which is an epoxy-based adhesive for the epoxy box bar demonstrator, and then there's an acrylic-based adhesive called Bostik for the helium demonstrator. And then on the side here we have the glass fiber epoxy demonstrator, a section view, and we also have the glass fiber helium demonstrator, a section view of those. The 2 main differences between the geometry and all the components are the same, except the metal inserts or the T-bolts. So this one is a carrot-shaped insert, and it has a tapered design. So there's a larger diameter at one end and then a smaller diameter at the other. So you have to have a machined tapered hole, and then an allowance for a bond line to bond those inserts in after the component is manufactured. Whereas the T-bolt is a different design. It has a barrel nut and a bolt. So they're just and it's attached to the root end by drilling a straight hole down through the top of the spar cap to house the barrel nut, which is glued in place, and then a straight hole in from the root end, which just to allow the bolt to be fastened in place. So that's the main 2 differences between the 2 spar caps, as well as the material, of course. Demonstrator molds then, this is just simply how we manufactured the surfaces that we use to manufacture the components. So we have a steel plate, a flat steel plate, and then we have a C-profile web to make the web components. And then molds are prepared with release agents so that when we infuse them, they don't stick to the base plate or the web mold. Then the demonstrator web manufacture. So we started off with laying up the dry glass fiber. Then we laid down the consumables, which are a peel ply and distribution mesh in white and blue. And then we have the vacuum bag and the resin pot and feed tube. So that's where the resin will be sucked into the component, and it'll wet out and it'll go towards the vacuum pump. And then these are the completed webs. Once they're demolded, trimmed, and dimensionally inspected. Then moving on to the spar cap, we have the layup process, which includes the peel ply and distribution fabric again to allow the resin to flow efficiently. And then we have the dry glass fiber plies stacked up. So there's a good thick section there of glass fibers, and it tapers off towards the tip. Then this is the VARTM or infusion process. So we have the resin feed pots all along the sides, and all of the kind of maze of tubes are all the resin feed tubes to get the resin into the part. And then you have the vacuum bag, of course, then covering everything. And so then this is what the completed spar cap looks like once we demold it and take off all the consumables and vacuum bagging. Demonstrator assembly. So first we apply the adhesive to the bond lines, and then we place the two C-profile webs in position. And then finally we bond the spark cap to the webs. And then I have some real photos here of applying the pressure. So once we have the webs bonded in place and the spark cap bonded in place, we apply some weight on the top just to consolidate the adhesive. So once it's all post-cured, it's ready for the CNC where the root holes are machined. That's to take the root inserts, the pirate-shaped root inserts or the T-bolts, and then installation of the inserts or T-bolts. So you can see in this image here, in the bottom right, that the barrel nuts are here on the piece of paper, and the bolts themselves are at the back. And then we just put the barrel nuts into each of these holes, glue them in place, and then we pass the bolts through the holes at the root end, and they just screw into position. And then we have the two completed demonstrators of the glass fiber epoxy demonstrator on the left and glass fiber helium demonstrator on the right. You can sort of see a color difference. The epoxy one is a little bit greener, and then the helium one has more of a yellow tint to it. So now I'll hand over to Yadong for the structural testing of the demonstrators.
Okay, so after you manufacture the demonstrator, so we brought it to the large structures lab in the engineering building of the University of Galway, and try to apply a vertical load on it and to study its structural responses. And this data will help us to find some defects of this structure and obtain some testing data for calibrate your numerical model, and that will be prepared for the design and optimization of the full-scale wind turbine blade. Okay, so just mention that Conor presented the manufacturing of the two demonstrators, but actually the real timeline is that he first manufactured the epoxy demonstrator, then it was brought to our lab to some testing. Then we found some aspects that we can improve. Then we manufactured the second demonstrator, that is a helium one, and we will test and try to see if this type of recyclable composite material will be suitable for manufacturing large-scale composite structures like the wind turbine blades. So here I will present the testing of an epoxy demonstrator first. And regarding the test, what we are going to do is we are going to test the electrical frequency and apply a vertical load and study its response under static tests. So for the natural frequency test, we use the impact hammer to apply a transient impact on the tip of the demonstrator. Maybe it's under free vibration, and we use accelerometers to record this vibration and use fast Fourier transfer analyze to get its natural frequency. And this natural frequency can be used to indicate the stiffness change of this demonstrator. And secondly, after we complete the natural frequency test, we just apply a vertical load here at the tip to push the demonstrator down, and this will give us the responses of the displacements and strain on the composite structures. And based on this data, we can analyze the structural performance of this demonstrator. So this is a whole test setup. The demonstrator is mounted as a cantilever beam, and at the supports you have several very heavy steel components to fix its root, and at the top you have 250 hydraulic actuators, and to apply the compression load through the extension bar. And along this bar cup, we have several strain gauge and displacement sensors installed. And during the static test, we applied 4 load cases until the failure occurred, and I will go through it later. So here is a video showing show our tests. So it's a speed up video to show the failure of this demonstrator. But actually, I'm not sure it's moving. Playing here, but you can see slightly it's just going down, and at some parts you see there is a failure occurred at the root of this demonstrator, and that is a failure of the steel part, which is the steel inserts. So now I will go through the test results. So first is the natural frequency in clockwise and edgewise direction. And secondly, it's a static test. And we found the first damage in load case 3 and a load of 24 kilonewton. And we hear the sound, and there is a slight drop on the loading. And then we decide to load the demonstrator to fail in the last load case. So ultimately, in load case 4, the demonstrator failed at a load of 30 kilonewtons. And actually, it's not a failure of this composite material, because when we started the spring on the spark up, we found this spring quite small compared to the failure spring of the composite material. And the real failure is put out of the steel inserts. And as you can see in these two pictures, so that means the bonding springs between the steel inserts and the composite material is not enough. And that's why when we are manufacturing the second demonstrators, we change a different connector, which is a T-bolt connector. Anyway, so now when we have the test results, then we utilize the test data to generate an element model of this demonstrator. So it's a combination of solids and shell elements, and this model includes every component of this demonstrator, includes the composite parts, steel parts, and the adhesive, and everything is modeled in software ANSYS. And when we are comparing the numerical model predicted natural frequency, and we see there is a difference of roughly 30% to 36%. And we think this difference was due to the flexibility of the supporting structures. So when you are trying to heat this demonstrator, actually the support will move a little bit, and this small movement will introduce some error in the natural frequency test. And we also observed some root rotation during the static test, which can support our conclusions. And in terms of the prediction of the spin and the deflection, and we see that for deflection, we have a good agreement of under this in the first 3 load cases, because for the first 3 load cases, we don't have any damages in the composite material, and we can have good prediction. And in load case 4, since there is a internal damage, mainly is on the root support, sorry, on the steel insert in the root. So there will be a slightly larger difference in the test between the test and the numerical prediction. But if we take a look at the spring, you will see for all the load cases, all the springs agrees well with the prediction. And the only exception is the spring on the root parts, because for the root parts, it's very complex. You have your adhesive, you have your steel inserts. So it's very hard to predict the spring on around the root parts. But apart from that, we can see for all the 4 load cases, we have good agreements. And that means there is no damage in the composite parts, and the weakest part of the demonstrator is a constraint system. Okay, so that's why we, in the second demonstrator, we use a T-bow connector, and after manufacturing, we repeat everything again. Then need to brought it into the lab, do some natural frequency tests, and do some static tests. And we also learned a lot from the previous tests. So in this test, we improved a little bit, but everything is quite similar compared to the previous one. In terms of the load cases, instead of increase around 10 kilonewton, we decrease the loading steps so that we can get more data. And apart from that, the locations of the strain gauges are almost the same, because we are using a different connection system. So I put 2 more strain gauges around the T-bolt, the head of the T-bolt, to measure the strain. And regarding the loading applying mechanism, it's the same. And here is a slide summarizing the testing of the second helium demonstrator. And this demonstrator should be fully recyclable. And as Conor said, by doing the mechanical test, there is no significant difference between the glass epoxy and glass helium. And this reflects also in the test results. So the natural frequency is 14 Hertz, and compared to the previous epoxy demonstrator is 13 Hertz. So it's quite close. And similarly, we have similar stiffness for the 2 demonstrators, and I will mention it later. So just here is just some observations we observed during the loading. So since we decrease the load steps, so we observe the first damage of this demonstrator and a load of 36 kilonewton. And this damage is also a damage of the steel component, not the composites parts. So it's a nut damage here. So we observe some nuts get damaged, and we have to replace it. And so considering that we want to break the composite material, so we just add more nuts around these ports and repeat the last load case. And in the last load case, we also observed the damage of the steel components, which is a tensile failure of the T-bolts, as you can see in this photo. So under extremely high tension, all the T-bolts get tensile failure. And if we compare the failure of the nut, that is 36, and the failure of the T-bolt, that is 35. So they will roughly fail at the same time. So we can see, okay, the weakest part of this demonstrator is still the steel part, and we didn't find any composites damage, which is supported by the measuring of the strain gauge. So all the strain gauges, if you check the strain volume, that's much more less than the failure strain of the composites material, and indicating that it's the composites material are safe. And in terms of the deflection, so we have 9 deflections, and if we compare the deflections of this helium demonstrator, which is recyclable, compared with epoxy demonstrator, which is not recyclable, we found the deflection before failure, it's roughly, I wouldn't say it's exactly the same, but it's within the same range. So this indicates that both demonstrators have similar stiffness, and that means it is very promising to replace epoxy with helium to manufacture some recyclable large composite material, composite structures. Okay, so now when we tested when we manufactured, tested two demonstrators, and we validated that it's possible to use recyclable composite material to replace the conventional non-recyclable composite material. And we have our numerical model validated. So now it's a good time to start design a full-scale wind turbine blade. And in this case, we are targeting on this Vestas V27 wind turbine, which is 225 kilowatts wind turbine, and the blade length is roughly 13 meter. So that's a reference blade, and here is a whole procedure of designing and optimizing the efficiency of the wind turbine blades. So in this case, we are caring about too many things. So we are designing for an existing wind turbine, so we don't want to increase the length of the turbine. So that means we can only change the aerofoils and the geometry of this wind turbine, and to improve its power generation efficiency. That's the first objective. And the second objective is that try to increase its strength, and possibly try to reduce the material used in manufacturing, and that can save some manufacturing costs and would be quite would contribute to the sustainability. Yeah. So first step is optimizing the power production, and here I used the blade element momentum theory to simulate the operation of a wind turbine. And here is the simulation. This blue line is the simulation output from my model, and the black dots are obtained from the testing of the real wind turbine. So you can see there is a very good agreement with each other, and we proving that we can use this type of model to predict the power production of this turbine. And in the optimization, we consider the changing the foil shape, change the size, and when I mention the size, I mentioned it's a change the width of the foil and the twist angle of the foil, and try to capture more wind energy. And I used the genetic algorithm combined with this with the numeric model to get the optimized blades. So after some optimization studies, we obtained 4 different blades, and the reference one is the lowest one. This power curve is here, and for the blade 4, which contains different oil, different size, and different twist angle, it has a better power production efficiency. So overall, it will have roughly 3 to 4% of annual 4% more annual power production. And these figures use the shape comparison between the reference blade and the optimized blade. After we got the external shape of the blades, then we try to design its internal structures. And here we use the ANSYS software as we used before. And besides validating the model using the testing data from the demonstrator, we also utilized the testing data we obtained from the previous testing, which is a full scale of 30 meter blades, to further validate the numeric model. And we get good results in terms of the deflection and strain, which enhance our confidence in this finite element model. And during the optimization, we considered the different a lot of parameters. The first one is the size of the spark up, which is the main component of the structure. And we also consider the number of the composite supplies or at each location. So there are a lot of parameters involved. And regarding the optimization methodology, I use the screen methods combined with the Horton sequence to generate a lot of blades parameters. Then we just analyze every parameters and we can select one or two optimized blade design from this randomly generated data. And the optimization objective is the blade, increase the blade stiffness, reduce the material usage, and also increase the strength of the blades. So here is an analyzed result. So we generated 1,000 different blades internal design, and we analyzed these 1,000 blades under the same node case. And here is a plot showing the mass and the deflection of the blades, and each dot represents the performance of a single blade design. So from that, we selected one blade which is close to the lower bound of this scatter, and this one has a balance of weight and deflection. So the weight will be a little bit smaller than the reference blade, and the tip deflection will be much smaller than the previous one, and which indicating there is a good increase in stiffness. And this shows the analysis of the stress and the geometry of the spark up and the thickness of the spark up of this optimized blade. And then after we got the full design of the geometry and the internal composite materials, then we can start to manufacture the blade. I will hand it to Conor for the details.
Yeah, once I received the mold or the blade design, the final blade design, the next step was to manufacture new tooling or molds for the wind turbine blade. So if people don't know what a mold is, I'll just describe how you can achieve one or attain one. So you usually start off with a mold pattern or a plug, which is usually in the shape of the final component that you want to manufacture. So the top surface would be the same as the wind blade skin. So what you do then is you'd manufacture a mold, which is that gray component there on top of it, to take the shape of your component. So then you demold your mold from the pattern or plug. You flip it around so you can start laying up material inside. So that's your component, and then you demold, and then you have your component. So they're the main steps, and I'll show you how we did it at full scale for the 30-meter wind blade. So for this project, we had to manufacture 4 molds: a pressure side skin mold, suction side skin mold, pressure side skin mold, suction side skin mold, and then we had the leading edge web mold and the trailing edge web mold. So I'll give you an example of mold manufacturing process for one of the skins. I think it's the pressure side skin. So we started off with an MDF block. So we just glued a load of MDF sheets together to create the plug block or the pattern block. We put it into our 5-axis CNC machine, and we machined the surface of the wind blade from that block. So that's our final pattern, which you can see completed here. So we made 6 sections, and we glued them all together. So you can see in this image here, there's 2 nipples, and then there's 2 holes on the other side, so we can locate them and make sure that all sections are in line. The next step then is obviously gluing each of the sections together, and then we seal the surface. So to try and get a really smooth, clean surface finish on the MDF, and also so that when we are making the mold, it's not going to be absorbed by the MDF. So we sealed it with some gel coat, and then once the gel coat was set and polished, we started making our mold itself. So we reinforced it with some composite material, which is glass fiber and polyester resin, and then we put some stiffeners on the back of it, which you can see these yellow stiffeners here. And then once everything was set and cured, we demold it and polish the actual mold surface itself. So you can see here in the bottom right the completed mold skin ready for manufacturing the skin component. So then I'll talk about the actual skin manufacturing process. So you can see a CAD model here on the left. So these are all the plies. There's about 80 plies laid up into the mold here. The first two plies were triax, and they went down. So you can see here, this is the first dry glass fiber ply being laid up into the mold, followed by the last glass fiber ply being laid up into the mold. And we can see here the rectangular section running down the spine here is the spar cap. The brown section here is the balsa wood, which is used to just stiffen up the skin panels or skin plies, because they're only a couple of mil thick. And then the final ply going across all of the rest of them. So these green plies here is essentially that last ply that's going to encapsulate all of these spar cap plies. So then the VARTM process, or the infusion process, the vacuum bag is in place, and all the resin pots are ready to go as well. So we'll fill them up with resin, and then we pull a vacuum. So we draw all the air out of the vacuum bag, create that pressure differential, and then the resin then will be sucked into the parts. So I'll show you a quick time lapse, and you should be able to follow the resin. The resin will start penetrating from the root, and then you'll see it slowly move up the blade. Hopefully you can see it all right. So you can see it getting darker. And then come to the end then, where we do the final checks, make sure it's all wet out. And then the final image here on the right, is the demolded or ready to be demolded skin. So you can see it's a completely different color. It starts off as your white dry glass fiber, and then once it's impregnated with the resin, it turns a kind of a greeny color. So that's ready to be glued together. But we can't do anything without the webs. So I'll talk about the webs next. The CAD model on the right shows the number of plies that we laid down onto the mold. So they're a mixture of triax in blue and unidirectional glass fibers in gray. So you can see in this image here, the dry glass fiber ply layup has started. And the next image then, the consumable layup. So we can see the peel ply, which is white, and the pink is a release film, and then the blue is your distribution fabric. Same as before with the 5 meter demonstrator. Next we have the VARTM process. That's the exact same as you saw in the previous slide. The resin just penetrates so that it changes color. And then the vacuum bag and obviously resin pots, feed tubes are ready to go. And then once it's done, it's completed, we rip off all the consumables and the vacuum bags and we demold it. So you can see that's a bit of a sharp angle there. It's kind of looking up underneath to see that sharp edge. And that's basically the flange that we're going to use to bond it to the spar caps. And then that's a completed web. So the other skins and web components were completed in the exact same fashion. So then we're moving on to the wind blade assembly. So this is just a quick kind of CAD versus real imagery comparison. So we start off with the wind blade skin in the mold and the webs ready to be bonded in place. So we apply adhesive to the two web flanges. And then, so you can see here in that image that's just popped up there, myself and my colleague Tommy were applying adhesive along the flanges using a pneumatic applicator. So we just put the adhesive cartridges into the gun, and then there's an airline hooked up, and it squeezes or pushes the resin or the adhesive out onto the flanges. Then you can see the arrows. Then we just flip the blades into position. So you can see there, the CAD model, the two webs are positioned in place, glued in place, and it's the same here on the right as well. The two webs have been glued in place. Once they're set, then we apply adhesive then to the leading and trailing edges and also the remaining flanges of the webs, which is also carried out in that image there. I think we're setting up to go gluing. And then we bring the the suction side skin, or sorry, the pressure side skin over, and we position it in place, and then we apply pressure. Pressure application for the full scale blade was used with ratchet straps and timber, just to try and evenly apply pressure across the bond lines. And then that was left in place then for about 24 hours to cure, and then it was put into an oven for post curing. So we demolded it, took it out of the mold, and then we wheeled it into the oven in the background. So we have a 16-meter gas fired oven, so we can cure out of autoclave quite large structures. And 30-meter blades, 14-meter blades is actually the largest we've cured in there. So then moving on to the final assembly part, which is step 6, we CNC'd the root end. So we just drilled the holes so that we could start installing the T-bolts. And then once the T-bolts were installed, you can see them there in the last image. The blade is essentially finished, and you can see it here on the right, the complete recyclable, sustainable 30-meter wind blade. It's suspended there, right on the center, center of mass, and we were weighing the blade there to get the overall weight of the blade. And you can see how stiff it is. It's able to support itself on a really small strap without bending or flexing. And then that's the team of engineers and technicians that helped to get the blade fabricated. And then it was shipped off to the university, which I'm going to hand over to Yadong. He's going to talk about the structural testing.
Oh yeah, so after the manufacturing of these recyclable wind turbine blades, then we brought it to the lab for testing. And then it mentioned that based on literature review, this wind turbine blade can be, maybe it's the first recyclable or first thermoplastic wind turbine blades that was manufactured and tested, and which is a big bonus for this project. Okay, so now similarly, we repeat the testing procedures, but here we have one more test. So besides natural frequency test and static test, we also perform the fatigue test, and the fatigue test is try to simulate its working condition and make sure that it can work safely within its operation life. And after the fatigue test, we will repeat the static test to check if there is any change in the responses, and any change can indicate that there is some fatigue damage during the fatigue test. Okay, so this one is a 30-meter blade, and it's far more complex than the demonstrator. And here we used a lot of spring gauges, as you can see here on the upper sides, lower sides, leading edge and trailing edge of the blade to measure its responses. And besides that, there are two load points to apply the load to simulate this wind load for the wind turbine blade. And besides, it's different from the previous demonstrator test. So here we didn't use the actuator because it's a 30-meter long blade and it's quite flexible, and the stroke length of the actuator is not long enough for this deflection. So here we used 2 chain blocks to apply the loading, and between the chain block and the load points, there is a load cell to measure the load, and this clamps is CNC'd using MDF, manufacturing using MDF and CNC'd to ensure that it matches well with the blade surfaces. And besides the spring gauges, we also use the fiber optical spring gauge to measure the development of spring along the blade. Okay, so now what we in the static test, we planned for 7 load cases, and in the initial static test, we will just perform the first 4 load cases and load its blade up to 7% of its design load. and because we don't want to break it, because we need to complete the fatigue test. Then after fatigue test, we'll repeat the static test and load it up to design node. And it survives after the design node, then we increase at 10% of the design node until the failure happens. Okay, so now here is the testing results of the initial static test. So 4 or 5 load steps, and here we didn't capture any deflection after the load case 2 because we reached the measuring limits of the displacement sensor transducer. So here, if we are missing points here, but when we are looking at the strain development, we found the maximum strain is around 3.5 at the location of 3.5 meters from the roots, and this maximum strain is far less than the failure strain of the complete material. So we can see that there is no failure at 70% of the design node, and then we can continue with the fatigue test. So for the fatigue test, we tried different loads mechanisms to simulate the working conditions. So we used the electric motor to rotate, and on the motor there is an unbalanced mass system on it. So when it rotates, it will generate vibrations up and down and make the blade vibrate. And here I showed 3 different radios, and different radio represents one fatigue load conditions. So for this one, we have 2 electric motors and a mass mounted at the middle of the blade. And here it's vibrated a little bit smaller than the other one. And for these 2, they are just there is no mass attached to the blades, and only the rotor. And here is a single rotor, and here is a different rotor. So we tried different rotating speeds, different mass, different locations of the motors, try to achieve the best answer. And this one was done by my colleague Kieran here, and he did a lot of works in the fatigue test and also in the static test. So here, as a result of the fatigue tests, as I mentioned, we use this kind of unbalanced rotating mass system. And here is the procedure of these springs with the increase of the fatigue cycles. And we reached 5.5 million of cycles, and we observed that there is no obvious damage on the complex material, but there is the damage on the steel support at the end. So actually, the steel support experienced the fatigue damage, and that means there is no meaning to continue the fatigue tests, because otherwise the steel support will fail first before the blades. So we terminated at 0.5 million cycles. And then we repeat the static test. And in this case, we try to load it in the first trial. We try to load it at up to the 100% of design nodes in 7 node cases. And here he shows a speed up image video of this testing, and you can see there is quite a lot of deflection at the tip of the blade, but we didn't observe any failures of the blade, which is a good thing. And after that, we analyzed the deflection and strain data. So compared to the previous static test, we carried out more load steps. So there is an increase in the strain, but in the same as the previous test, the maximum strain occurred at the 3.5 meters from the roots. And if we compare the deflection and strain readings with the static test before the fatigue test, then there is no significant change of the strain and deflection. So that means there is no damage, almost no damage during the fatigue test, which is a very good thing. And after that, we decide to continue the static test. And here we load up to 100% of design nodes and increase at the 10% step. And finally, we broke it at the load, which is 60% to 70% of the design, higher than the design node. And at that point, there is a failure, complete failure at the distance, which is roughly 3.5 to 4 meters on the root. And here is a video shows the moment where the blade broke, and you can see there is a huge amount of energy released on the complete material. Okay, so here are the failure mechanism of the complete material. So here is a failure, and it's a fiber failure of the glass fiber failure at the center of the part. And besides that, there is a leading edge separation at the same location of the hole. And the trailing edge also separated because these two are bounded with adhesive. And if we look inside this, inside the blade, we can see there is a backing of the web. So the web also failed. And there, here you can see the damaged adhesive of these two bonds, these two components. And besides that, we also observed failures around the load points because we experienced a very high load, and there is a separation on the trailing edge. That's mainly the adhesive. And besides that, at the leading edge side, we also observed a crack on the root of the blade, and we believe it's due to the cracking and shocking of this complete material in the middle. So this location is roughly 3.5 to 4 meters from the root, which is a good thing because we observed the highest strain around the 3.5 meters. So that's the final results of the final static test. So you can see it has a very high deflection. So at the last 3 steps, we get out of range of most of the displacement sensors. You can just capture 2 points. All these are out of range, and we have one displacement transducers damage due to the breaking and the energy release of the blade. And if we compare the strain between this test and the previous static test, we didn't see a lot of changes in the strain, and all these data points are least before the failure. So that's comparable. But if we compare the displacements, we found there is a slight increase in this deflection. So we need to dig out more testing data to find what happens between the two residual strength tests. But anyway, since the failure occurs at the 70% more than the design node, so it is a very good design, and we are satisfied. So I just make a summary of what we have done in this project. So we manufactured 2 demonstrators and 1 full-scale wind turbine blade, and all these blades are two of these components are recyclable. And then we performed the corresponding 3 experiments tests to validate the design, and the recyclable full-scale wind turbine blade shows a very good structural performance. And we also developed numerical models to optimize the blades, that the whole procedure can be applied to any type of blades, any length, onshore or offshore. So that's a good thing. And the most important thing is that we found it's very promising to use recyclable composite materials for designing this design and manufacturing the wind turbine blades. and Conor will highlight the challenges and recommendations in the future.
Yeah, so throughout the project, we came across a few different challenges. I didn't mention them while in the previous slides, but Yadong actually mentioned a few of them involving the epoxy demonstrator and the helium demonstrator. So the carrot-shaped root insert on the epoxy demonstrator, we made a machining mistake or machining error where we drilled a straight hole instead of a tapered hole. So that meant then that when we applied adhesive to bond the steel root insert in place, there was a lot of adhesive in at the inside of the hole and not so much on the outside. So there was a huge variation in the bond line thickness, which ultimately leads to like a weaker bond line. So it's really, really important that you machine, if you're using a tapered insert, you machine a tapered hole to ensure that you get a consistent bond line that basically means an even thickness all around the components you're trying to glue together. Similarly, then the root insert surface preparation that also contributed to premature failure. So we saw that when the root inserts were pulled out of the 5-meter demonstrator, they were really clean. There was no adhesive residue on them at all. We sandblasted them with a soda medium, and it just dulled the surface, but it didn't really roughen it up as much. So the surface energy could be increased a little bit more. So if you make in future in a future project, we'd prefer to make the inserts as rough as possible to try and maximize the surface energy and then improve the bond. Then in terms of the helium demonstrator, we saw that the failure again was in the T-bolts. The reason behind that was the tensile strength was lower than expected, so we should have preheated or heat treated the connector bolts to try and improve the tensile strength. So that's what we do going forward, and that's what we did do on the 13-meter blades. We learned from that demonstrator test. We got the full-scale T-bolts heat treated, and you can see that there was no sign of failure, even though it was loaded up to 160% of the design load. Then the wind blade manufacturing. So this is another significant learning curve. So when you're infusing with two different materials, depending on the process, you may have to infuse at like full vacuum for epoxy, which means you're infusing at 1,000 millibars of vacuum pressure. But for helium, it's recommended to infuse at 750 millibars. So it's 3/4 of a full vacuum. That means the consolidation pressure is a lot lower. And yeah, so that meant that we miscalculated the cure ply thickness for the 30-meter blade, and that resulted in a significant additional weight. So we added in, we did a thickness trial where we compacted a 40 mil thick section, and then we calculated how many plies are in that under full vacuum, but we didn't do it at 750 millibars. So we put in more glass fiber plies than we needed, and that increased the weight of the blade significantly. And that's probably why we didn't see much fatigue failure in the blade, because it was a lot heavier than we expected and a lot stronger than we anticipated. But it does show that the fact that it was a lot stronger means there's a lot of room for reducing the weight of the blade and optimizing the layup. So yeah, in future, we're going to carry out thick section infusion trials at different vacuum pressures to determine the effect on cure ply thickness, and hopefully that will solve a lot of issues. And then the wind blade testing fixtures as well, had premature fatigue failure, so hopefully in future we'll carry out some weld inspections, and hopefully we can run the fatigue tests up to 1 million cycles. That'll be the goal for the next project. So yeah, I think that's all from myself and Yadong. And these are some of the funding bodies: Sustainable Energy Authority of Ireland, Marine Institute, and Science Foundation Ireland as well.